Good friend. Okay. So in the morning we like you heard about glass transition a lot. Srikanth talked about little bit, and then went into discuss jamming in a somewhat different perspective, and then Ranjini talked about glass transitions in Laponite and also aging. But in this talk I will discuss glass transition from liquid side when the liquid is approaching. Is it okay or is it echoing too much? And we already know that from the discussion it was felt, you probably already realized that glass transition itself is a issue which is not been resolved, and there are lots of debates and there are lots of questions, and it's not clear whether there is a transition or not. And in the today's talk, so this random pin has some hope to give us ideal glass transition, and I will tell you some of the works we have done along those lines. So first couple of slides I can easily skip, but if you want I can go through it, but I think it's better to skip it because you already heard about all of this. Cool the liquid rapidly, go to a glassy state, and viscosity goes up many orders of magnitude if you change the temperature by few degrees. And also the typical correlation function shows some characteristic property which are not seen in normal liquids. So this dashed line will be for a normal high temperature liquid, that is like a normal exponential relaxation. But if you go to supercooled liquid which approaches so called glass state, then it has a two-step relaxation process. One is very fast, which is, so this stage which is somewhat ballistic, which is not of very importance, it's not very important, and then there is an apparent plateau. Plateau is not a real plateau, it's actually slanted. So there are relaxation happening, and that's a regime which is called beta relaxation, also very controversial, and these things are not very clear, and then eventually the correlation function decays at longer time scale. Sorry. So that's called alpha relaxation time. Okay. So there is a clear cut difference between a beta and alpha is not very clear, as you probably saw already in Ranjini's talk, but I will be in this talk I will be only focusing on alpha relaxation, and then the related story. There was a cat. Monkey. Okay. He also interested to do glasses, yes. Okay, so the other puzzle is what is the glass transition problem itself. If you take a liquid cool rapidly, then over this temperature range you see that this was like a melt, and then you go to a glassy state. The typical pair correlation function, the structural property does not change significantly. So this curves are shifted just to show you that there is hardly any difference. But then if you calculate the viscosity changes by many orders of magnitude, actually goes from something like 10 to the say order 1, let's say from here, or 10 to the minus 2 to something like 10 to the 12 or 13. So 14 orders of change in viscosity without any significant change in structural property, at least in 2-point correlation function. So that's the puzzle. So this is known as the glass transition problem, and it's not clear whether there is a glass ideal glass. We made some recent progress with Itamar, but to be able to show that there is a static length scale which is growing by at least factor of 5 or 6, but that's a different story. But maybe we can discuss later. And so there are so what are typical glasses? That includes many things. There are metallic glasses which are been used also in day-to-day life. There are granular packings, emulsions, colloids. This picture is taken from Rajesh's talk, and this is computer glasses. So in this talk I will try to get some information by doing molecular simulations, and try to see whether some information can be extracted from these systems. Okay, so now come to the random pinning. So glass itself is complicated and we don't have much idea, but now I am adding random pinning site. So what are random pins? So this is, let's say, a typical glassy configuration. You need to have two types of particles at least to have enough structural disorder, so to avoid crystallization. Okay. and top of that now you choose few particles randomly. So these so I just black dots are the randomly chosen particles by hand in this case, just to demonstrate, and then you pin it. The meaning of pinning is that they are frozen in time and in space, they cannot move anymore. Okay. So immediately this system loses its translation invariance. So you have a Cohen's disorder in the system, and this normal system will not have that. So in normal glasses you have anneal disorder, and this one randomly pinned system will have a Cohen's disorder, which also breaks the translation symmetry. And the hope is to, and there are a couple of works also, some of by us and Giorgio Parisi, and we showed that this system has similarity with spin glasses, P-spin model system, and maybe it has some transition, but that has to be looked at carefully. Yes.
When you choose these random pins, do your results depend on the correlation between the pins? Suppose they were not random, suppose if I put it in that case.
So it seems it does. So there are, so I will show some results from Walter Kopp where they chose the pins in a different way, and that those numbers are different, but qualitative physics doesn't seems to be, but in terms of numbers they will be. But if I now put let us say a really ordered array, then it may be different, that we don't know right now. Yeah, so that I will come and so another issue is which is important here, that you take this disorder configuration liquid state and equilibrate at some temperature, and then spin particles are chosen from that configurations. Okay. So I don't have enough time to give you analysis or a discussion over disorder physics, but when you study a system with Cohen's disorder, one has to do something called Cohen's disorder averaging. So instead of thermal averaging, not instead of, in addition to thermal averaging, you have also Cohen's disorder averaging. That is equivalent to saying we are choosing different pin configurations and doing averaging on those. Okay, so you have to do two types of averaging to get a reliable, to get your data. So this is one such correlation functions which also what Ranjini showed is from let us say intensity correlation function from DLS. In our case, this is one such overlap correlation function, and as you go to lower and lower temperature, you see that the nice plateau appears and the relaxation becomes sluggish. It takes longer and longer time for the system to relax. Now you compare this with the spin system, where I kept the temperature at some number, and then I am increasing the pinning fraction gradually, and then you also see that it has very similar effect as like this decreasing the temperature. So what it does, it increases the typical relaxation time. Okay, and you can now easily imagine that if I freeze everybody, right, then there is no relaxation. So the question becomes, is there a possibility of getting completely stuck or ideal glass state by freezing finite amount of particles, finite fraction of particles, okay, not 100%, less than 100%. And there are a couple of mean field analysis and some approximate RG calculation done by Giulio Biroli and co-workers, and they seems to claim that indeed that's possible. And I will just briefly go through those spin glass type calculation in an infinite range model, and also what are the prediction, and then I will come back to this liquid system with pin particles and show whether what's the difference between those results. Okay, so basic idea is that just by pinning particle you can increase the relaxation time, and the hope is to reach ideal glass just by introducing pin. Okay, so the issue is, so one important point is that if you want to reach ideal glass by decreasing temperature, then the relaxation time becomes so large that you cannot equilibrate the system. You can't actually go to, if the glass exists, You can't reach there. Before that you will run out of your time and you will go into non-equilibrium state. But here I am choosing the spin particle from an equilibrium configuration, and just by increasing that number I am just gradually I am just increasing the corresponding time scale. I do not have to do equilibration again, right. This is very important here. So, I do not have to do re-equilibration. I just start from a unpinned liquid and freeze freeze some particles, and then the corresponding the time scale of that corresponding pin system will be larger than the unpinned system. And the point is, if I just increase the spin fraction to certain critical fraction, will I completely freeze the dynamics. In that way I am just bypassing the slowing down and then just reaching the glass state just by doing pin, which does not involve equilibration further, but it requires also to do disorder averaging. So that is equivalent to doing like you do ensemble average instead of time average. Okay. So that is the idea. Okay, let us go through some of that mean field calculation done by Chiara Camarota and Giulio Biroli in this PNS paper in 2012. So they took I think the p-spin model and also some random energy model which can be solved exactly, but that is in the mean field limit, and found that if you calculate this is another term which I need to describe. This is Srikanth did not describe. So this is something called configurational entropy, and that is related to, in some sense, the amount of accessible phase space you have. The log of that gives you the configurational entropy. Okay, so basic idea is that you calculate. So configurational entropy is given by this SC is like you calculate the bulk entropy, and then from there you just subtract the corresponding crystal entropy. Okay, let us just to put in a simpler way, but this is somewhat more tricky. And what in those mean field calculation gave us is that the configurational entropy with pinning actually goes down from its unpinned value. That is something which is expected, right. If you have a system where and then you free some degrees of constraint, then your accessible phase space will be restricted, and it is natural to assume that your configurational entropy will go down. Okay, so that is but then the specific details of this y of t actually is very important. So here it was chosen that this configurational entropy with pinning will be will go down linearly with pinning density, and y of t will be a weak function of temperature. Okay, but it may but that this is the part which is not very clear whether this is indeed true or not. But if you believe that this is true, then you see that just by changing pinning concentration, assuming y to be weakly temperature dependent, you can go to a pinning concentration where this SC T comma C will go to 0, right, and that number will be this SC T divided by y. For each temperature there will be a pinning concentration where there will be this quantity will go to 0 if this linearity holds all the way up to all values of C. So this may be true for small pinning concentration, but this is what is been assumed, and then you see that if you calculate those configurational entropy and where this quantity goes to 0, you will have relaxation which is infinite, right. If you do not have any accessible configuration, you are stuck to one state, you can't access any other state, then you cannot relax. So that will be your ideal glass. So if you have ideal glass, then your configurational entropy will be 0, right, log of 1 will give you 0. And so this is the, so if you just assume that this linearity holds, and then you can calculate the corresponding temperature as a function of pinning concentration, and that they found that this temperature where this will happen will go up gradually. as a function of pinning concentration, and so this is in the mean field limit. So the point is that the temperature where so called glass transition happens goes up to a higher and higher temperature with increasing pinning, and then if this phase diagram is correct, then if you are at some higher temperature somewhat here where you can still equilibrate your liquid nicely, then you just walk along this line horizontally. Okay, you just walk like this, then you will cut this glass transition line and you will be here in the ideal glass state. Okay, so that was the proposal. And then also there was subsequent analysis which also predicts the existence of another length scale. No, these states are all ideal glass. So these are all ideal glass. So this is the ideal glass transition line. This is the fluid or the liquid part, and this is the glass state. If you are at a higher temperature when your pinning is very low, then you increase your pinning, then eventually you will hit this glass line, and you can actually be deep into glassy state by just increasing number of pins. The last point is something which is different. Let's not go into those, because even before things are not clear. So it also predicts there is one critical point where this glass transition line, and there is something called dynamical transition temperature which meets, and there is something, this point is called some A3 or A2 singular point, where glass will have different properties. So this I am not very clear about it. Anyway, also corresponding, they also did some approximate renormalization group calculation, which has been also questioned actually by I think Moore and company, and showed that those procedures are actually not correct. But also if you assume that they are even qualitatively right, then also they found that the glass transition temperature increases with pinning strength. Okay. So this mean field and RG seems to be giving you similar qualitative picture, though the curvature is slightly different, but let's not worry about that. And then there was a subsequent simulation done by Walter Kopp and Ludovic Berthier. So this is in 2013. So they looked at, they studied binary model system, which forms glasses. These are called Kopp-Anderson model. And then they pinned some fraction of particle and studied, calculated this spin glass overlap correlation function. Okay, and then from there, let's not discuss in details about what these quantities are, but but they calculated, they found out the corresponding transition temperature from. Yeah, this is something which is probably important to understand. Okay, so just to quantify where glass transition happens, so what you calculate, you just do spin glass replica calculation, okay, and then calculate overlap between two replicons, and and it was shown in spin glass system that it develops non-trivial distribution. So it was initially one Gaussian and eventually becomes bimodal. Okay, so that gives the signature of this is identical pinning configuration. Yeah. So yeah, I should have paid more attention while preparing this. This is a somewhat cut paste talk from a previous one, which is somewhat elaborate, which also discusses about what is replica calculation and what is replica symmetry breaking and all of that. But yeah, for this purpose of the talk, this will not be very important, let's say. So what they found actually numerically from somewhat noisy data and very small system size, that's another important point, actually 64 particle, that was in 2013. And they found that glass transition line actually indeed increases with pinning density. So, so that was somewhat similar to the mean field and approximate RG calculation. And then we thought let's look at this from a dynamic perspective for a bigger system size. And we did also simulations of this Kopp-Anderson model with let's say 1000, 2000 particles. and then also did all the pinning configurations up to 20%, and look at the corresponding time scale and calculated, then fitted it with Vogel-Fulcher thumb unfit, which as we discussed is not the ideal thing, but this gives you an upper estimate of a divergence, is actually overestimate the divergence. So even if you don't have a divergence, this VFT fit will give you some number which is finite. So even if you have a let's say glassy state, a model system where you know that there is no glass transition, so the glass transition temperature is 0, then you calculate time scale as a function of temperature and fit VFT. VFT is something, yeah, I'll write it here. So VFT is this, tau alpha is tau naught e to the a over t minus t naught. So this is what also Ranjini showed, and if you fit your time scale data over a finite temperature, then you get some t naught which is non-zero, even if you do it for a model system where you know that t0 is 0. Okay, so Vogel-Fulcher always gives you overestimate. So it cannot, so whatever divergence temperature you get, it cannot be worse than that. Okay, so if you just, so we naively repeated that analysis, and VFT fits are reasonably nice for all pinning densities, and then we calculated the corresponding phase diagram. So calculated the divergence, VFT divergence temperature as a function of pinning density, and it seems the divergence temperature does not depend on pinning concentration. So by the way, as I was telling you, that this is the worst possible case. You may not have any glass transition, but it cannot be worse than this. And there, here you get from a somewhat bigger system size that this apparent divergence temperature is very insensitive to the pinning strength. So this became a surprise for us, because what Walter and Ludovic showed is that indeed the TK calculated from a different point of view or via different calculation was actually increases, right. From the dynamic perspective, though it is a fitting extrapolation, it gives us something which is contrary to that, it is actually very opposite. And also in the same time we realize that with pinning the fragility of the system changes very rapidly. Okay, so this is this angel plot where this is without pin, then as you pin the system, this system becomes more and more strong liquid. So one point I told you that if you have a system where you have constraint and without constraint, in two cases the constraint system should have less configurational entropy. That is the thermodynamic constraint that you cannot violate. But then people will say that now if you go on adding many constraints, then you should actually freeze your dynamics. So this is thermodynamically not consistent, but you can actually show that this is still thermodynamically consistent. There is nothing which stops you from having this picture where divergence temperature does not change with pinning, but fragility changes. How obvious?
Well, you know very well that the reason in these models that you have the strong increase in tau alpha is because they get longer and longer regions that are needed in order to have a relaxation. If you pin particles, you cannot, because it stops the elongation. So clearly you're going to become more strong, so to speak, because you cannot do this. So though, see, all these fragilities is angel bullshit. It just says that the slowest mechanism becomes slower, right? And the slowest mechanism is because you have larger and larger regions that need to be cooperative in the dynamics. This is why you get an effective increase rate, an effective increase.
No. Fragility I don't agree, because fragility you see here, right? There are the way it changes is different.
Fragility exists because when you decrease the temperature, you need larger and larger regions to cooperate. That costs more. So your energy in the sense of E to beta E, is increasing the energy there. And now you break it simply by putting pins.
No, no, but yeah. So
Not
that's
about
okay.
this
Yeah,
mechanism, that's it.
yeah. No, but in general, fragility exists. That you
I'm
don't.
saying fine. I'm just saying that I'm not surprised by this.
Okay, good that you are not surprised. You are also not. But then, yeah.
Instead of pinning single particles, can you pick
Regions
regions?
of chunks. So for a very big system size, that should be equivalent.
Because it is diverging anyway.
Is diverging anyway, so in some sense. But that is something for the kind of system we can study. There, if you just pin a chunk of this, I don't know what will happen. You can try.
It's a really stupid question. So you see, you take parts plate products,
Yeah.
they form these layer masses. So then if you have a softer potential like the one with green split 4, 5, 6 years ago, squishy nephalites,
Yeah.
they form these stronger classes. And that he says is because of the fact that squishiness gives you some direction in the bonding. That's the way at least he wraps up towards N.
Uh-huh.
So when you're turning on random pins, if I were to think of it in such a way, how do I visualize it? Like if I were to have a particle in glass compound, which all I do is pin particles,
Hmm.
say R4, R2, how do I visualize it as a consequence of the direction that the product is long division of the
That, yeah, I don't think that's a unique mechanism of. So this what is fragility is actually not very clear, and how do you understand it? I will give you some way of connecting this to our favorite length scale, but that you may not agree. But there is some connection to the length scales and cooperativity, so that will become apparently clear. Will become clear. So this we studied for two different model system, where you take. So just to show that this does not depend on what model system you take, is generic
As long as these are point particles.
as long as these are point.
Point particles. Now it's important. Because of this, you don't have change in the time. You cannot have an infinite time scale in point particles. Because you can, every temperature, you can always have fluctuations that all the particles.
No, but that's going back to whether you have a finite temperature divergence or not. This analysis does not depend on all of that. We are not claiming this.
So there's no finite temperature
Yeah.
divergence even when it's spin.
Even without spin.
Even as long as it's spinning density is less than unity.
Less than
You
unity.
can always move the particles.
Yeah.
Because the point particles, they can always move.
They can always move over a time scale. So this is just to say that this apparent divergence, which is overestimation, that does not depend on pinning. So that's markedly different from the mean field model and the other simulation calculation. Okay. And then, so this is the rationale for understanding our data.
So we do have this length scale. I mean, broadly what you're saying is right, but the devil is in the details in terms of where you expect change of behavior and so on.
Correct.
So, but your data is sort of once you have a certain thing, it's uniformly.
Uniformly pinned, yeah.
Yeah, uniformly the dynamics is described by, or you're describing the dynamics by a different fragility, right?
Yeah.
So, but in principle, if the pinning is defining a length scale, when this intrinsic length scale crosses that value, you should see a change of behavior. Is that something that you have attempted to pull out?
I don't think we are in that regime, but reaching that is something which will be difficult. But dynamically it will be impossible, right? Getting a time scale will be very difficult. You can get static information. Calculating entropy and all of that will be fine, but then dynamics and the time scale you cannot get. Because just by pinning, time scale becomes so large that you have to have some correlation function to decay to give you some estimate, right? That is. So if you go to that low temperature where the length scale becomes comparable to the pinning length scale, and then there is a competition. So that regime, I think we are not there, but maybe with very large, around 20% pinning, we may be hitting those. That we haven't looked at probably very carefully. So this is just, so how much time do I have? 15 minutes. They are doing fine. So we just rewrote this entropy part. Before I was writing entropy as a, yeah, so this is important. So the mean field gives you entropy in terms of let's say T and rho. I am just omitting pin. That was like SC at T0 minus rho times Y, with Y of T was very small. And we believe that this has to be something like this. Is a multiplicative function f of T in rho pin, and f is something which is weakly dependent on temperature, but somewhat strong function of pin. And then in a linear order this will be obeyed, but then your y will become proportional to SC. Okay, so this actually, this is an observation. So this is what we are proposing. The SC T comma rho pin is nothing but the TSC at 0 pin, and then there is a function f which continuously goes down with pinning, increasing pinning density. And then if you use something called Adam-Gibbs relation, which connects time scale to entropy, it does not matter what is the actual relationship, as long as there is some relationship, this will hold. And then you just do little bit of algebra and calculate ratio of time scale with pin and without pin for a given temperature. And that if these are all correct, then it will be something like G, which is a function of rho pin divided by TSC0, and in a small pinning regime you can always write in a linear part, the first one is 0. And that so this function ratio of time scale with a pin and unpinned system will be function like constant times the pinning fraction divided by TSC0 particles. And so this is the figure you should look at. So here this is the configurational entropy plotted as a function of pinning density for a given temperature. You see, as you increase the pinning density, it hits 0 at some pinning fraction. As you do it for a higher temperature, this hits 0 at bigger pinning density. As you go to higher and higher, then the pinning required according to their calculation is becoming more and more. And but the point is that if you pin this much for a given temperature, then your entropy, configurational entropy goes to 0. So then you are stuck to one ideal glassy state. Okay. So that way, so they also then showed the phase diagram. And so this is the phase diagram. Again, it is the transition line seems to be increasing with pinning strength. So here the still mean field picture holds, and our analysis seems to suggest that this blue line should be something like this, horizontally. Okay. And then so unless our calculation is completely wrong, or there is some issue about this entropy calculation. So there is one thing which is clear, that there are anharmonic effects which has to be taken seriously, because when your entropy becomes very small, if you do not take anharmonic effects carefully, then you are playing with small numbers, and you see that your entropy actually becomes negative in places. And they also agree that there are anharmonic effects, but it is not clear whether if you just add anharmonic effects, whether this line will become parallel to this or not. So that is a debate which is not clear, but just to find out, at least we have some clue of what is happening. So we simulated the same glass with the same system size at these state points, where let us say given temperature, you around, let us say 12% pinning, entropy goes to 0, and at some other temperature around 15% entropy goes to 0. So you just pick up 4-5 state points where according to this calculation entropy has to be 0, so your time scale has to be infinity, and just we did MD simulations, and you see that the typical so these are for a couple of state points, and the corresponding time scales are not infinity, they are order of 10 to the 6 or 7 at max. So these are the system where you can, even in simulation you can equilibrate the system. Forget about in experimental time scale. Experimental time scale will be 10 to the 14. And so this is this is a puzzle which is not clear to us of which calculation is wrong, but or is there something else which is happening. But we believe that the picture we are getting, so this picture is consistent with our proposal where there is no ideal glass transition with increasing pinning, but also it contradicts the entropy calculation. It can also tell, it may also predict that or suggest that relation between entropy and time scale is also breaking down. But even if you have any relationship which is coming with, so the entropy and time scale relation is this: tau alpha goes like tau naught t to the power some a over tsc. Okay, so this is what is been assumed for Adam Gibbs. You can have any arbitrary alpha, beta or x or something, and then if this quantity goes to 0, the corresponding time scale has to diverge. It does not matter what form you take, even if it is only kind of power law, not even exponential, then also it will become very large, and our data does not seems to suggest that. 5 minutes, okay. And this is something, so Robert Jack and Ludovic Barther actually did some finite dimensional spin glass calculation with random pins, and they came to conclusion that mean field, MCT and RG calculations are qualitatively different from 3D p spin model, so which seems to suggest that our proposal is probably along those lines. But it still has to be understood why the corresponding entropy calculation was giving apparent entropy vanishing transition. Okay, but that has to be proved.
I can argue why it's privatized.
Ah.
I mean, you say that in your plots or their plots,
Yeah.
you say that the effect of the concentration on the configurational entropy is essentially linear.
Essentially linear here.
It goes down so linearly, and then at the end, who knows? But this linear thing, when we increase system size, the configuration entropy grows much faster than linear with the system size.
No, but this is configurational entropy per particle. So,
And that's not going to grow with the system size.
so here I don't know whether, so there are some finite size effect. Small systems it does grow, but it,
Grow. Right? I mean, of course, in the thermodynamic limit, it's a number. But when you increase from small systems to small to large systems,
Yeah.
the increase in the number of configurations is so huge that I believe that your concentration will have to become larger for the same temperature in order to get this zero SC.
No, but,
so there is a competition here between system size and concentration, which I think
it's not obvious. So generally the configurational entropy grows SC as a function of n. It's a whatever temperature range we can study is something like this, where by around 1000 or 2000 particles this is already saturated apparently. Okay.
But here you also as you increase C, effectively you're pouring in water. Or if the configuration
Yeah,
can instead will become
much more
some
how extensive. So then, so this figure has to become like this. So SC as a function of pin, here I am writing as rho, it has to go down linearly and then has to do like this, and then it has to go to 0 at pinning 1, because there is nothing, and everybody else has to do something like that. And there is no thermodynamic constraint of to have this picture, and whether there is error or yeah, this is something which is yes.
They find out SC by subtracting two quantities. So that is always a problem.
Yeah, no, that's why there is
S1 by thermodynamic.
thermodynamic integration.
Both the quantities are got in by numerics.
sure. Of course.
So when this becomes small or
But there are large fluctuations.
large.
Right.
Making that very
Okay, so we can go for a anyway. Yeah. So also like so here, so let's say this blue point. So this blue point is at around temperature 0.5 and your pin is around 15%. There is a perfectly nice liquid where your correlation goes to 0 so smoothly that.
Look, if they get negative numbers, why we should believe the zero? The negative numbers are absolute bullshit, right? So why the 0 is not absolute bullshit?
But in the your Mexico meeting, have you asked the same question?
Not in this language, but yes.
Okay. Yeah, it is somewhat informal. That's what I am asking this.
So Walter agrees with this size issue, but he doesn't know. All the calculations are small systems. Walter is very honest. Very honest man. He's Swiss. No, really. Very honest. But he doesn't claim more than what
The data shows.
numbers are, you know? And he accepts that there are issues of accuracy, system size, these nerves about the negativity. No, he just says, look, this is what we do.
Okay, fine, fine.
And I think it's not a final statement.
I should.
One is the much larger systems, which are very difficult. What's about?
Okay, the last point about. So this is the experimental realization what Rajesh they have published, and also probably will be trying harder to do something along this line. So even their data shows similar behavior, so which is encouraging. And some fragility can be understood if you invoke something called RFOT theory, which Itamar again will not like it, but assume that there is something. Okay, so it connects length scale, just 2 minutes, I will just finish this. Length scale connects to configurational entropy via some exponent, and then you rewrite, so then this was already I wrote before, then you just do some small pin concentration approximation, and you can rewrite your length scale for the pin system in terms of your length scale which is unpinned system. This you can actually calculate from a different calculation. So that is information I know, and then there are this pinning dependence. Okay, so then there is A is some parameter which I don't know. That's one number which I fix, and then I assume this functional dependence between tau alpha with length scale, and this is the unscaled data. And this is the data which where the length scale is calculated via this approximate method. This I pin by T, which seems to be bringing everybody into the master curve, and the same thing true for the other model system. So the length scale, static length scale has something to say about the fragility, and that cooperativity and all of that seems to be. So this is something which I feel nice, because that in some way supports the static length scale and the other length scale which we are proposing, and understanding glass in a somewhat unified way. So, and thanks. I think there are. This length scale, just the pin system I don't know, but that I use RFOT to rewrite in terms of pinning approximately, and so this is the length scale for the pin.